So we are now getting to our last big unit, combinatorics and probability. So last time we ended with a puzzle about, well, chocolate again, and this puzzle asked about how many squares of chocolate can you identify on this piece of chocolate. And if you attempted to just say, oh yeah, this is 4 by 4, 16 squares, well, that's true, but you could also have squares which are 2 by 2, 3 by 3, 4 by 2 by 4. So the question remains, how many squares here if you count squares of all sizes? So let's figure it out. So there is one big square which is 4 by 4. That's just the whole thing. There are 4 squares that are 3 by 3, and the way you could see it is look at this blue outline squared. This is one. You could move it one up, that's the other one. You could move it one to the side, that's another one. Or you could move it one diagonally, and that's another one. Alternatively, you could think about it as there are 4 choices for the top left corner of the square, which gives you the 4 squares of size 3. How about squares of size 2? Well, if we again use the top left corner idea, now there are 9 possible top left corners, the 4 that we had before, plus 1 row and 1 column, which give us 5 more possible starting points. So now we have 3 choices for row, 3 choices for column, 9 choices. And finally we get down to the smallest square, and this one, probably one of the ones that you counted first, is a 16, 4 by 4. So overall there are 30 squares on this piece of chocolate. Suppose we have a much bigger piece of chocolate, so how do we count the squares here? Well, there's still one square, 13 by 13. Then how many squares? 12 by 12. Well, we have 2 by 2 starting point, 11 by 11. We have 3 by 3, 9 starting point, and so on. So in general, if you start with a piece of chocolate which is n by n in size squares, then you end up with the sum of the squares of numbers from 1 to n, and this will give you the number of all the possible squares. Okay, so what does chocolate and squares have to do with this course? Combinatoric is a really big part of computer science because a lot of time you need to count things, and you already encountered it in a bit of a disguise because when we were looking at sets and countable sets, we had to, well, count numbers, and we kind of brushed it off a little bit to this part of the course of how we would count, for example, all strings of length 1, then all strings of length 2, and so on and so forth. Also, when you are looking at the programs and trying to determine how efficient they are, how long they will run, one of the immediate metrics is when you're solving a problem, if you know how many possible solutions there are, well, then you know how many solutions you need to go over and check whichever one works. So this will give you an estimate on how long the program will run. So for example, for sorting elements in an array, we know exactly how much time a program should take because we could count how many possible outputs it can produce given a specific input. And another part of the combinatorics comes in a lot is cryptography, because there, if you have very few possibilities, it's easy to iterate over them, and no matter how secure your system is, if if somebody knows that you have a 4-digit PIN and they can look at all the possible 4-digit numbers, well, then they could find whichever one works. Mind you, when you're doing it with ATM, it only allows 3 tries until it locks the account, so that's not going to work that easily. But ideas like that play an important role in various break-ins and prevention of break-ins. So you may be wondering, is it better to ask everybody to have a password with digits and capital letters and lowercase letters, or whether it's better to ask people to enter a passphrase which may contain just letters, but which would be a lot longer? So what do you think is more secure? Well, by the end of this next lecture, you will have the tools to actually figure it out. And another part of combinatorics is counting things in more complicated situations, because sometimes some of the possibilities are indistinguishable from each other, are identical. So maybe there are several different passwords or strings that all have the same hash. And if you only look at hash, then the string it came from are indistinguishable. So you want to really count the possibilities differently in case when some of them are lead to identical outcome. So one example, which you're probably not going to consider in full detail, is counting things like trees or other data structures. So for example, maybe you want to say that those two graphs here are identical because all of them consist of just a sequence of one vertex connected to another, which is connected to third, which is connected to fourth, and no other connections. And you could convert one into another by turning it around and maybe moving things around, but not disconnecting and reconnecting anything. So this is another thing that you may be wondering, how would you count stuff like that? So we would start with two of the main rules for counting things. And those are the rules that come from the chocolate puzzle. And they're the rule of thumb and the rule of product. The rule of thumb says that if you have two things, A and B, and you have n ways to choose A and you have m ways for B, then there are n plus m ways to choose A or B. So for example, going back to the chocolate, you have squares of size 1 or 2 or 3 or 4. So the number of all possible squares is the number of squares of size 1 plus size 2 plus size 3 plus size 4. That's the rule of thumb. So OR of things gives you sum. Now an AND of things gives you product. If there are n choices for A and m choices for B, then there are n times m choices for A and B. For example, A can be your row and B can be your column, and what you're counting is something that's in row A and in column B. So if there are n rows and m columns, it would be n times m possible places, so you will get n times m possibilities. So let's get back to our security motivation. So suppose you look at pin numbers consisting of 4 digits. How many of such numbers are there? So here we could use the rule of product, because we want a number between 0 and 9 in the first digit and something between 0 and 9 in the second, n in the third, n in the last one. So if you look at all the possibilities over the sequence of 4, it's 10 times 10 times 10 times 10, 10,000. But 10,000 is not such a big number. By the pigeonhole principle, even at MAN you could find more than 10,000 people, and so you could find, well, probably, maybe you cannot find them, but it must be people with the same pin. It's enough to have 10,001 people to have guaranteed 2 people with the same pin. So this rule of product comes up a lot when you have a sequence which has n places. For example, if you're doing a truth table, you have n variables and each variable has 2 possibilities. So how many choices you have for a line, for an assignment, how many lines in truth table you're going to have. Well, it's 2 by 2 by 2 by 2 n times, so it's 2 to the n lines. So in general, if you have a string of length n such that every letter in the string has m possibilities, you get m to the n possible sequences. And another way of looking at it is you could think about it as Cartesian product. If you have a set of options for the first digits and a set of options for the second digits, then you have a set of pairs of options, one for the first and one for the second digit of the pin. Or if you're talking about, again, chocolate squares, you could have rows and columns, and then you could have pairs, an index of a row and an index of a column. All of those are examples of Cartesian products, and now we could just say that the size of the Cartesian product of several sets is the product of sizes of those sets. So for example, here is a puzzle. Suppose you come to some kind of eatery in the cafeteria, and they say you could make your dinner out of 3 types of protein, say meat, chicken, and falafel, 2 types of starch, noodles and rice, and 4 types of sauces. How many different meals can you have from this place? Well, it's 3 times 2 times 4. So let's look at a slightly different example now. So we have, our department has, let's say, 20 faculty offices in the engineering building and 4 more in the earth science building. Say we have 24 faculty members. So how many ways are there to get 4 people to go to earth sciences? And how many ways to actually get specific offices to those specific people? For example, Oscar, me, Joandra, and Dave are the 4 people who are going to earth science. Well, now there are 4 offices. How many ways can those 4 offices be assigned to the 4 of us? And then you could ask the joint question, how many ways there is to select for people to go to earth science and assign them to the offices. And this is what we will talk about next time.